It really depends on the symmetry of your coffee. Because if this coffee had a chiral P wave or chiral D wave symmetry, then, and it was a superfluid, then actually the moment that this coffee was brewed, it would have a whirlpool. It would have this orbital angular momentum. And you might think I'm just doing crazy talk here. That's a weird thing to bring up. But I'm not talking crazy. This liquid, this fluid, it does exist. I knew symmetries were important when I did my master's, and I took a course on symmetries in quantum mechanics, and I don't think I learned anything at the end. I mean, there wasn't a single particle or anything that's remotely related to physical world mentioned there. It was just basically pages of math after math or so. But if you want to be, and the only time, other times it actually pops up usually is in, you think it's in the context of particle physics, neutrinos and so on, because each of them, their wave function has a certain symmetry, and that symmetry kind of tells you what kind of system you have. What does your wave function look like? Does it have angular momentum? Does it have spin? Is it, there is a lot that could happen in this wave function. Now, we've already introduced superconductor. We already said that you have now a many-body system with a, simple, elegant wave function. So you can have study a single wave function on a macroscopic scale. But what I didn't tell you is that these wave functions also can have all kinds of symmetries that can be extremely exotic. But let's start with the basic categories of symmetries in superconductors. Let's say we want to talk about some of the major, there's type 1 and type 2, and I think this is more important. This is more fundamental to classify superconductors based on the symmetry of the wave function. And the first parameter we're going to look at is the spin. Right? We're going to look at the spin symmetry of a Cooper pair. Now, when you think of Cooper pair, how do you imagine the spins? Yeah, you basically think about a Cooper pair. You think about one electron being in a spin up, the other one being spin down. And this is called singlet pairing. It's a singlet state, and it has, zero spin. It's one spin up and one spin down. This is how you write. But can you have the other way as well? Can you have, is it allowed, first of all, at all?
So yes, it still works.
Right, okay, good. I'm glad, actually, I was waiting for that question. So this is where I need you to bear with me. True, we're Cooper pairs, we're dealing with bosonic system, but, this is not a system that we had intrinsically boson. We had to make the bosons out of fermions. So in order to form the Cooper pair, you still need to follow a certain principle. What is it called? Exactly. So once you form the Cooper pairs, once the Cooper pairs are formed, then it's fine. You're dealing with bosons. But in that initial state, like this transition to go from forming bosons out of fermions, you need to respect this Pauli's principle. And then it comes to the question of, is this equal spin type of pairing allowed? The thing is, actually Pauli's principle doesn't say anything about spin. What it says is that your pair function, when you basically form this pair, your total wave function of this pair needs to be antisymmetric or, odd. Remember the odd and even functions? So this is the even function. If you fold it on top here, you have even, and this one is odd. You're all familiar with this? Good. So you have odd or even. Now here you have, usually in most superconductors, you have odd spin symmetry. So one spin up and one spin down. But now, there is more that goes in the wave function, right? So it is allowed, and this is called triplet superconductivity. You know why it's called triplet? Obviously, there's 1, 2, 3 of them. Do you know the difference between these states? Right. So basically, once you develop a spin, you have 3 possibilities, of what this net spin of 1. See, all these 3 states have a spin of 1. But then the question is, which way is this spin pointing? And to do that, you always need to define a quantization axis. So whenever you think about spin, it only makes sense if the spin up or down, it has to be with respect to what? Some axis. So here, for instance, we pick Z to be our quantization axis. Sometimes, usually it's the axis along which you have, you can induce some difference between different spins, like with the magnetic field or with the exchange field of the ferromagnet. That could define your quantization axis. So in all cases, you have a spin of 1, but projection, this spin projection, that has 3 possibilities. It could be -1, so we're down, +1, or 0. So you could also have a spin of 1, which is basically perpendicular to your spin quantization axis. So that's why you have these 3 states. But the bottom line is that now you have electrons paired up with a spin of 1, and this is called triplet superconductivity. So why is it allowed? We talked about spin, but there's other ways that you could make this wave function antisymmetric. So just think about it like if you want to write a wave function, want to describe a wave function of 2 electrons, right? What are the things you need? So, okay, their spins is one of them, but how else? What are the other parameters you need to use to describe the system? Yes, exactly. So position or reciprocal. So real space, position of space, but the reciprocal of space. Again, this is something that you could go. It's like a 1-to-1 relation between reciprocal space and real space. So you could have odd parity, they call it, or let's say odd momentum part or odd spatial part. Now, this is where you end up with different possibilities. So these are the, let's say, called S wave, D wave, P wave, and so on. Now, do you remember these shapes, S, P, D? You've seen these before, right? S orbital, P orbital, D orbital from quantum mechanics, chemistry and stuff, atomic orbitals. But here we have nothing to do with actual atomic orbitals. These are just conventions that we're borrowing from, atomic physics, atomic orbitals, to describe what this wave function looks like, both in real space and momentum space. So if you have a so-called S-wave superconductor, that means when you form a gap, your gap is uniformly formed around the Fermi surface also. Yeah? And this along any direction is going to have the same magnitude. And also, if you go from one point to another point, let's say if there is, by elastic scattering or something, you don't change the sign of the wave function. The sign of the wave function is the same. So here the colors are actually the sign of the wave function. But if you have D-wave symmetry, here, that means you have what? You have a 4-fold symmetry system. First thing that happens is that your amplitude of your wave function actually develops some nodes. So along certain directions, your superconductivity gets weaker. And the other ones as well. I mean, it's not completely 0 because of some scattering, actually, this part gets a bit blurred. But there is a very pronounced anisotropy as you go along this direction to this direction in the superconductor. They have they have an anisotropic gap. So some directions, your superconductivity is stronger than the other one. Yeah. Oh, the hole is just basically there because it's supposed to be like, let's say, the Fermi surface or around the gap that forms around the Fermi surface. It's not so. We're talking about a gap here, right? Because if I didn't, then it would just be. So this is like literally what your Fermi surface, what your gap would look like if This part was just the, below the firm surface and above the surface. Yeah, like literally this is, if this is your firm surface, you start forming a gap basically around it with these different lobes. I mean, that's the whole point of using these whole conventions, because S and PD and their combinations are a very convenient way of doing it. But this is really, we're talking about momentum space. And of course, not all Fermi surfaces are this symmetric and spherical. Sometimes there are, sometimes there aren't. But the whole point is that if you reduce it, the symmetry, which one of these is going to be, right? So here, D-wave, you have a 4-fold symmetry, right? And you also notice that you have different colors. So if you go from this K value to this point, which you can actually do in a real experiment, this is one of the exercises, you gain a phase of pi. And then you have a P wave, an F wave, and so on. And now some people getting very desperate to describe asymmetries of some of these superconductors. I think we're up to G wave now. Yeah, we have G wave symmetry.
We are talking again about the global wave.
Yes, there is no atomic orbital here. This is just a convention. This is just shows you what does the gap, if this was the Fermi surface, what would the gap look like around the Fermi surface? That's what this is, basically. And if, for instance, there was an elastic scattering that you went from this point to this point, what would happen? Because in this case, or in this case, for instance, if you have this elastic scattering, suddenly you have a plus and minus pi, they cancel each other, and you actually get rid of your gap. So these guys, they're very sensitive to defects. But that's besides the point. Is this so far okay? Because, I mean, this shouldn't be, if it looks complicated, then I'm doing something wrong, because it's really just about.
I'm still getting used to looking at the wave function in momentum space, because also in the previous slides we always used psi of r.
So I'll make it easy for you. You can directly translate to real space.
Sure, but this.
So if a wave function,
The symmetries in real space would be different.
No, none at all. Wait, I'll show you experiments. Actually, I'll show you one now. So we just talked about this little Parkes experiment, right? Or this fluxo quantization loop, and how you could have this piece of ferromagnet there, right? Well, there's another way you could do it. Suppose you have a crystal with this D-wave symmetry, right? So here, I'm really bad at drawing, by the way, as you can tell. Okay? So you have an actual crystal. I mean, this is something we've done in the lab. So, and you go and make a connection from here to here using what? Just a conventional superconductor. We call this a corner. Well, it's a corner squared, but I haven't explained what squared is. Basically, make a loop. So here's this normal superconductor that connects this to this side. And guess what happens? You end up with the pi phase shift. Exactly. You end up, or to put it differently, you end up with a qubit, if you like. You end up with a superposition of both clockwise and counterclockwise because of this phase shifter. This becomes your pi phase shifter. Instead of so I said about a ferromagnet being there, but you could also use one of these, actually, to get to that point. In fact, the reason we know, I was going to say which one ought to be 20 is even, but I think it's clear at this point that S wave symmetry is even, and P and F are odd. So P especially is very sought after these days because of its applications for quantum computing and Majorana physics and this topological states. But in fact, actually, this is the experiment that showed that cuprate superconductors, the ones with the copper oxide, have a D-wave symmetry. They did something very similar to this, only they just used a single cuprate. So they actually arranged these crystals. So they made a ring out of 3 different crystals with different orientations. So I'm not going to go through all these, but basically here you see that you're going minus to minus, and then here basically going to minus to plus, and then you're going plus to plus. So when you go around in the ring, you end up with the net phase shift of pi, which means that now your orbital phase only needs to wind by half, at 0 field basically. So you have a half quantum vortex. So this is also very important that, so basically the current generated by the field flux generated by your current is half of the magnetic flux quantum because you've already compensated half of it. So the only thing that actually coupled to the external magnetic field is the orbital phase. But if your order parameter has this intrinsic phase shift in this orbital phase, for instance, then your magnetic flux that comes out of your system is only half of the fluxoid value. Is that clear? Good. But as I said, so this is, as you see, it works in real space too. It's not a trick. Okay. Now we're going to, how much time we have? Okay, we have 20 minutes. That's not bad. We might even get to the good parts, even better parts. So we covered spin and momentum, or which was orbital symmetry, if you like. But now there is a third option. There is another blurred picture here. What's that? What goes there? Yes, exactly. Time, or if you like, frequency. So this is, now this is something that, when I started my PhD, it was right at the peak of all this controversy about whether or not this can exist, this thing. And I would go to these conferences, and now we know it exists. My students make them all the time. We have basically, it's, but at the time there was like basically 3 groups in the world who could generate this type of symmetry. But the fun thing is I could not get a right description, like an intuitive picture that I could explain it to people. Like, what does that mean that you are in time? Okay, orbital, spatial part I can get. Well, what does it mean that your wave function is antisymmetric in time? And, well, mathematically, it actually makes, it's very simple because there is a thing called the Matsubara frequency, and that, if it's basically antisymmetric, you're good, you're done, But it turns out that if I really push theorists to really give me a straight answer, give an analogy, they don't agree on their analogies. Well, the ones I came up with, I'm happy with, and again, I have some theorist friends who don't like it, but who cares? But anyway, so it's that, it boils down to the fact that the 2 electrons need to avoid each other somehow. They have to avoid each other in spin. If they can't, they avoid each other in space. If they can't do that, they avoid each other in time. So I think of it as like a timeshare vacation apartment where the 2 electrons kind of occupy it, but at different times. Nevertheless, they're paired with each other. Nevertheless, they're kind of in a bound state, which is this apartment. Better way to put it, maybe, is that the 2 electrons that, there's this correlation function that pairs these 2 electrons together. And this correlation means that there's a correlation time. And under the exchange of this time coordinate, your wave function flips its sign. Because there is a finite time that needs to, you're going from one coordinate to another. So this correlation time, basically, under the exchange of this correlation time, you flip the sign of your wave function. And these are, let's say, pick whatever you like, But this is, as far as I can basically simplify. Yeah. So we kind of just summarize it, wrap it, give it a bit more structure, because whatever we discuss actually leads to, well, 2 main categories, which we could say singlet and triplet pairing. And in each case, you could have 2 scenarios. So the first case, I'm going to actually do this. So most of the superconductors actually we know, both conventional superconductors and unconventional superconductors, both low temperature and high temperature cuprates, they all belong to this category, where you have antisymmetry in spin. So you have even frequency, even momentum, but your spin is on. Now, this category is kind of like nobody talks about it, and I don't know, it's kind of a black sheep. It's not even clear that this would be energetically, stable, like thermodynamically stable. It's allowed. I should say that, according to Pauli's principle, this is definitely allowed, but whether or not it happens or can be, that's a whole other story. Then we go to this triplet category. There we have dealing with a very, very few materials that actually show this symmetry. The first one was actually that they discovered was helium-3. And funny enough, at the time, there was two proposals for describing the wave function of this helium-3. One was by Anthony Leggett, which actually proposed the odd parity, so P-wave symmetry. And the other one was from Brzezinski, who proposed the odd frequency. And, well, it just turned out to be odd parity, so Anthony Leggett got a Nobel Prize, Brzezinski didn't get anything. But then fast forward, this was 76, so fast forward literally 3 decades later, they found these correlations at the interface between superconductors and ferromagnets, sort of by accident, mind you. So just to kind of come to it, this is very rare. We only have a few materials. Actually, I spent a lot of time during my PhD on strontium-ruthenate, which was the prime candidate for triplet with P-wave pairing. It turned out to not be triplet, but that actually made the matter a lot more, weird. So it's one of those problems that's been going around for 30 years now, and it just, basically it's a reset button. But we still don't know what's going on, what kind of symmetry this material has, but we'll come to it later. So there's a select few of these materials, and they only appear in very clean systems, because actually if you have a system where where the phase actually can change its sign in K-space, if there's elastic scattering between, then you could end up canceling each other out. You could end up basically suppressing the gap. So your mean free path needs to be much larger than the coherence length. The coherence length, you could also think of it as the size of the Cooper pair, or the minimal size of your condensate, basically. So this happens in ultra-clean material, but this guy actually, they popped up at the interface between the superconductor and the ferromagnet. Good. So one thing that I should mention, that I said that there's 4 categories, but you could always have, mix and match. You could have a hybrid of different symmetries. For instance, this is the famous example of a chiral P-wave state, where basically you get a px plus or minus ipy, and basically this combination gives you a gap that doesn't have a node, even though, remember when I said that, hey, P wave or D wave, you could have nodes? Well, depends how you add them up, because in this case, you actually don't end up with, anisotropic gap. There's no nodes if you add these two together. But one thing that is interesting, one thing that makes it very different from S wave is the colors here. These colors correspond to the phase of the gap. And you see, this is a very weird scenario, but basically, you're not going from blue, red, like the other one. You have a continuous winding of the phase as you go around the Fermi surface. Now, that what does that mean? And there are two different possibilities. So you can have px plus IPY and px minus IPY. Now, maybe I'll come back to this in a lecture later, but this I is what makes this, basically, what would be the fast way to say it? This I ensures that you're not in a superposition, that actually there are two separate states. Because a lot of times in superconductors end up in being a superposition of one, let's say, one orbital and the other orbital, and you end up with zero orbital angular momentum, for instance. Like a D-wave superconductor does have an orbital angular momentum, but you don't see it because it's always, most of the time, you don't see it because it's a combination, it's in a superposition of plus and minus one. I'll cover this in the next lecture when we talk about a D vector, which is a little bit more rigorous way of thinking about the symmetry. But this I is what makes this chiral. It's also what makes, it's what gives you a doubly degenerate ground state. So you're not in a superposition anymore. You have two possibilities, and they correspond to which direction the phase of your order parameter winds.
Why is it degenerate? Don't we have to choose if we add or subtract?
Yes, so basically by the degenerate, I mean, normally you have one ground state in a superconductor, there's single ground state, right? Everything, all Cooper pairs go in one. Now in this case, your Cooper pairs have to choose to be either in px plus or minus. They can't be in both states. That's what I mean. So they have to choose one or the other. And that makes, we'll come back to this later, but why is this called a chiral superconductor? Well, it has to do with this phase. Because what's going on is that your phase of your order parameter is now winding, and could wind in the opposite direction, clockwise or counterclockwise. Okay? And you guys remember what phase winding produced when you had a phase gradient? What did that lead to? Current. Yes. So in a way here, your Cooper pairs, so where does that current come from? A lot of times people also confuse this with edge currents and stuff. No, here the current comes from the intrinsic orbital angular momentum of Cooper pairs. So it's a crazy scenario where all Cooper pairs are actually rotating, going clockwise or counterclockwise. They have this built-in kinetic energy that makes them go round in the left or right.
It's a ballroom dance.
It's
a ballroom dance.
It's a ballroom dance, or yeah. I guess that's a very, very cute way to put it. Yes, it's a ballroom dance. So now, but this is basically and I want you to basically just take a moment to think about this, because it shows you how important symmetries are. If I had this, let's say, this coffee in my hand, right, and I don't have a spoon, but what I was going to do, if I have to use to just stir it, so I have a whirlpool in this coffee, right? Now, if, for instance, you didn't see me stir this, and then you just came in the room and this coffee had a whirlpool in it, you would be like, well, somebody stirred it. Your coffee is not in its natural ground state, right? You would be right. But it really depends on the symmetry of your coffee. Because if this coffee had a chiral P wave or chiral D wave symmetry, and it was a superfluid, then actually the moment that this coffee was brewed, it would have a whirlpool. It would have this orbital angular momentum. And you might think I'm just doing crazy talk here, that's a weird thing to bring up. But I'm not talking crazy. This liquid, this fluid, it does exist. There is a fluid that if you pour in this cup, it would have a built-in whirlpool in it, and it's called helium-free.
The A phase of helium-3 is a superfluid where, with the built-in kinetic energy, it has a natural orbital angular momentum. So we're used to thinking about stuff being, and I mean, you wouldn't question an electron in an atomic orbital to have a built-in orbital angular momentum. That's quantum. But we have a hard time usually, to picture that on a macroscopic scale. You say, okay, that's the stuff that only happens on an atomic scale. No, not if you're dealing with a bosonic condensate. A helium, you could have literally an entire superfluid where the ground state, the natural state, is the one where all the fluid is actually winding clockwise or counterclockwise.
So what does it determine which one it is?
What do you mean? Which way they wind? Mm-hmm. Well, both of them could happen. So you cool down, it's going to be one or the other.
Right. But
yeah.
And they're going to be
completely another term. One of them would happen, and it would be completely random. Yes, completely non-deterministic. It's the same with superconductors, right? A lot of times, if you have actually the paper we just put out on arXiv, it's just about this. It's about a superconductor where you do have these chiral domains. They're not P waves, but they're another type of chiral. And you cool it down, and different parts of this crystal are just going to have one symmetry or the other. So it's like a magnet where you have domains, right? And within this domain, however, you have all the Cooper pairs winding in one direction or the other. And that is the natural intrinsic ground state of your superconductor. And it's happening, just because if one of your Cooper pairs has orbital angular momentum, all of them do. So that's what I mean by that's what's so weird about this state. So it's a macroscopic state with the built-in kinetic energy, where the ground state already has motion built into it. And I think we'll stop right after this. But funny thing, this is I've seen this now quite a few times where I'm at a conference and somebody said, well, we make this chiral superconductor. This is a chiral. They literally, you laugh, but seriously, you have no idea how many talks I've been to where they say, well, we have a chiral molecule, we printed a chiral chiral wire, and now we introduce superconductivity in it. Chiral superconductivity.
Technically.
Yeah, they're not wrong.
Well, in the case, that is the problem. See, it's a weird way of terminology. Then in that case, if I just get a piece of wire and then wrap it, then any piece of wire would just be chiral and a superconductor. Chiral superconductivity is not this. This is not, unless if your Cooper pairs inside this thing have an orbital angular momentum, this is not a chiral superconductor. I'm not saying you can't use this helical shape to create an orbital angular momentum for the Cooper pairs that could lead to chiral pairing. That might be a case, but you have to deal with the fact that let's say the chirality of your structure needs to be smaller or the same scale as your coherence level, right? So you need to, those are, otherwise anything, any wire that I just twist is going to be a chiral superconductor, and that can't be. Actually, Michel Orit, any of you have heard of the name Michel Orit? Well, he's retired now, but he still actually is emeritus at Leiden University. Michel had always this saying I like. He was like, every potato is chiral. Why should I care? So chiral, in a sense, is not really special unless if it means something for the wave function of your order parameter. Good. I think we'll leave it at this. Next lecture, we're going to talk about spontaneous time reversal symmetry breaking, and we'll take it from there. Good.